Welcome to the Road to 5G, brought to you by the Rogers Corporation. Today's topic, Key Material Properties for 5G, Part 1. Characterization of electrical properties used at millimeter wave frequencies.
Hello, my name is John Coonrod. I'm with Rogers Corporation. I'm a technical marketing manager. I'm going to be talking to you today about the road to 5G and specifically the key material properties in regards to millimeter wave applications. I'm going to have this video in two different segments. The first segment is really going to be geared toward insertion loss and different aspects of insertion loss. And then after that I'll be talking about more dielectric properties, dissipation factor, phase response, things like that. So to begin with, let's talk about insertion loss. As most of you know, insertion loss is made up of four different components. There's conductor loss, dielectric loss, radiation loss, and leakage. I'm not going to be talking about leakage losses today, and also not going to talk about radiation losses because that's more design specific. I'm going to be talking mostly about the dielectric losses and conductor losses. The dielectric losses, they're more related to the dissipation factor of the substrate and or the solder mask if that's involved. And then the conductor losses, there's many different variables there, but specifically I'm going to talk more about how copper surface roughness impacts conductor losses and ultimately has an effect on insertion loss. So with that, let me go ahead and show you a table of information that describes the introduction of this topic. Copper surface roughness will cause an increase to conductor loss, and also it has the ability to slow the phase velocity of a circuit. So for insertion loss, what I'm interested in is the copper surface roughness, and specifically the copper surface roughness that is shown in the drawing here, where I've shown a microsection view of a microstrip transmission line circuit, and at the interface of the substrate copper, that interface is what I'm talking about for the copper surface roughness. And it's that interface that is more problematic. If the copper is rough, it will actually slow the phase velocity and also will increase the conductor losses. Conductor losses in regards to copper surface roughness is frequency dependent, and what I mean by that is it's related to skin depth. Once you get to a high enough frequency where the skin depth is the approximate dimension as the copper surface roughness, that's when the copper surface roughness will impact the insertion loss by increasing the conductor losses. And also it will have an effect on phase response as well. The impact of copper surface roughness on insertion loss is also thickness dependent, and what I mean by that is substrate thickness dependent. So a thinner circuit is more dominated by the conductor effects than a thicker circuit. And this is shown in the following picture. In this graph I'm showing insertion loss comparisons using the exact same material. It's 5mm RO3003 materials, and I'm using copper that's different roughness. So we made these laminates with the same substrate but different copper types, and one is a rolled copper, which is very smooth, has a surface roughness on the average of 0.3 microns RMS. And then we also used another copper that was ED copper, and this particular ED copper has a surface roughness average of 1.8 microns RMS. And you can see the difference at millimeter wave frequencies, that there is a significant difference in loss. At 60 gigahertz or even 80 gigahertz, there is a remarkable difference in loss. But also keep in mind the scale here, that the 5mm RO3003 with ED copper having 2 dB per inch loss at 80 gigahertz is considered extremely low loss. And the rolled copper being at 1 dB per inch is also obviously much better than that. There are also other concerns for insertion loss other than copper surface roughness, and then one of them is plated finishes. And these plated finishes, there are many different types. There's ENIG, electrous nickel immersion gold, there's immersion tin, immersion silver, and each one of these finishes have their own aspect to insertion loss. They are actually doing something with the conductor loss portion of insertion loss, and generally these different metals have less conductivity than the copper, which increases the conductor loss. The chart shown here is a comparison between two different 5mm thick circuits that are microstrip transmission line circuits. They're both based on RT Doroid 6002 with rolled copper, and that's actually very similar in performance to the RO3003 materials. But really what I'm showing here is a difference between circuits that are built as just bare copper, so no finish, and then the other circuits are bare copper with ENIG on top of them, ENIG being electrous nickel immersion gold. And you can see there's a remarkable difference in insertion loss where ENIG is much more lossy than the bare copper circuits, and that's mostly due to the conductivity difference, where nickel is about 1/3 the conductivity of copper. There are also other issues associated with insertion loss, and one of them is moisture absorption. All materials that are used to make printed circuit boards has this property where they will absorb some amount of moisture just from the atmosphere. And obviously moisture or water vapor is polar in a molecular sense, and that does cause an increase of insertion loss. So there's different ways to characterize moisture absorption of the raw material or the circuit. And more commonly, lately anyway, is a test called 85-85, and that's really conditioning the material or the circuits in an environment that's 85 degrees C and 85% relative humidity for some period of time. And then what you do is you test the material or the circuits before and after this and see how the circuits of the materials respond. The chart shown here is a comparison of two sets of microstrip transmission line circuits. The first set of circuits is based on the 5mm RO3003 materials. And again, it's a microstrip transmission line, and the red curve and the blue curve is the difference between this circuit. It's a microstrip transmission line actually being tested at room temperature and then after being exposed to 72 hours at 85-85. And you can see there's a difference about 0.1 dB per inch at 79 gigahertz. Now the other set of information is the gray curve and the yellow curve, and that's actually a thermoset competitive material. And it's claimed to have low moisture absorption, but you can see by the response it really doesn't. And at 79 gigahertz, it's got a difference of 0.8 dB per inch of insertion loss when the circuit is tested at room temperature conditions and then later tested after condition at 72 hours for 85-85. Now there are other issues associated with copper surface roughness, and one of them is how the copper surface roughness actually impacts the phase response of the circuit. And essentially what happens is a rougher copper surface will slow the phase velocity of the circuit, and the circuit will perceive that as a higher dielectric constant. Even if the material stays the same for dielectric constant, a slower wave is perceived as a higher dielectric constant by the circuit. And that circuit perceived dielectric constant is what we call design decay, and it is sensitive to copper surface roughness. Now, at millimeter wave frequencies, this can be a very important factor to understand. So let me show you a little bit of information in the following graph. The chart here is actually showing a comparison of two sets of circuits. One set of circuit is built on 5mm RO3003 with rolled copper. The other set of circuits built on 5mm RO3003 with ED copper. So the exact same substrate, only difference being copper, and the rolled copper is very smooth, and you can see in this chart that it actually comes pretty close to a number of 3.0. I think out at millimeter wave it's about 3.03, but what that tells you basically is even though this is a thin circuit, the copper is so smooth that it's really not slowing the phase velocity much, so the circuit is actually reporting nearly the intrinsic value of the dielectric constant of the material. So this material, the Rogers RO3003 material, has an intrinsic dielectric constant value of 3.0, and the very smooth copper on rolled copper, using rolled copper, actually reports nearly that number. Then in the case of the blue curve, which is the same material, same everything, but different copper, and it's using ED copper that is rougher, that rougher copper slows the phase velocity, and the circuit perceives that as a higher dielectric constant. And here, at around 60 or 80 gigahertz millimeter wave range, it's actually a number about 3.2. So it makes a remarkable difference. And again, at millimeter wave frequencies, understand this effect and the copper surface roughness effect on the performance of the circuit and phase response can be very important. There are other aspects that can impact the phase performance of the circuit as well, and one of them is called TCDK. TCDK is an abbreviation for thermal coefficient of dielectric constant, and that's a property that unfortunately is often overlooked. And it can cause problems when that is overlooked and a circuit or an assembly is optimized in a controlled environment, and then it goes out in the field and goes through temperature swings. And what happens is every material has this property where the dielectric constant will change with the change in temperature. And that's something that needs to be well understood for many applications at millimeter wave frequencies. The chart shown here is actually showing the TCDK behavior of several different materials. First off, I wanted to point out the dark purple curve, and that's a material that's nearly pure PTFE, and you can see it transition at room temperature. And that's actually a pretty common occurrence for PTFE. That's kind of the nature of the beast. However, when you take PTFE and you do the right type of formulation, the right fillers, and you do the right things to formulate the laminate, what you can get is a PTFE-based material that behaves very well for TCDK, and that's the dark blue curve, which happens to be ceramic-filled PTFE, and that's the Rogers RO3003 materials. And you can see it's just about a perfect curve. A perfect curve would be a flat line at 1.0 on this chart for the y-axis, and that's basically saying there is no change in dielectric constant with a change in temperature. So 3003 has an extremely good TCDK, and that's one of several reasons why it's used at millimeter wave range frequencies. This concludes this segment to the Road to 5G. Thank you for watching.
For additional information and technical tools, if you're not already a member, Join the Rogers Technical Support Hub and gain access to calculators, technical papers, and more Rogers Corporation informational videos. Rogers Technical Information is also available at your fingertips with the Rog mobile app, available for the iPhone, iPad, and Android devices. Check it out today.